Hello, everyone. Welcome to 2021 Informs RAS Problem Solving Competition presentation. My name is Qing He. My team members, including Zhen Liu and Qingsong, we all from Southwest Jiaotong University from China. Our presentation title is Prediction of Estimated Times of Arrival of Freight Trains in U.S. Railroads. So here's our outline. So we have 5 components: problem statement, data processing, methodology, experiment results, and responses to the comments. So here's the objective. So we want to develop a predictive model that will forecast the ETA of a unit train of multiple car shipment at any point in this route. There are 3 prediction types. Prediction from the origin, from the middle way, and from the day before, near the destination. And there are 2 models requirements. The first one is base predictive model, so only use the railroad supplied data. The second one is enhanced model. We not only use the supplied data, we also use the GPS data. We try to evaluate if GPS is useful in this prediction model. Here's another special challenge, the study of partial shared routes. Because they are shared routes in the western and eastern regions, we call the west lane and east lane as shown in the picture. Share the same routes for substantial percentage of their overall movement for all trains in the west lane and the east lane. So we try to understand, is there any benefit from looking across different ODs in terms of improved ETAs? So here's the data processing steps. The first one is we did a data cleaning. So we remove the duplicate values. We remove the missing values, fill the missing values. Just remove the outliers and other types. And also for the category data, we code the category data. And for numerical data, we did a min-max normalization because we try to make the data in different range in the same. And we try to solve the problem of comparability among the data indicators. So here is an example of the before the processing and after processing comparison. So in the left is the before processing. You can see lots of outliers and some points out of the range of the plot. The after processing, you can see the data is more concentrated in a small range. For the next step is feature engineering for loaded directions. Loaded directions means the train is loaded with cargoes. So we have 3 steps. First, we select 12 features, and then we rank the importance of the features using random forest. And we select the top 7 features as the input feature of the prediction model. So those 7 features are highlighted in this table, including the remaining distance, the remaining stations, number of stations, number of cars, the arrival delays compared to a predefined timetable, and the total time traveled and total distance traveled, and the speed ratio to the average speed. Those 7 selected features. For empty directions, we did the same thing, and we also select the 7 features. The set of the 7 features for the loaded and empty are the same, just the sequence is different. For fifth one is for data selection for the special challenge. As there is no shared route in the south lane, so we only focused on this special challenge on west lane and the east lane. We also defined the different ODs for different lanes and for loaded and empty directions. As you can see here, we have 9 different ODs we defined in this following table. Our methodology is quite straightforward. We consider random forest regression and feature-weighted k-nearest neighbor for the predictive model, because we find these two models are most useful one among other models. For the random forest regression, basically it is a very prevailing, well-known method. It's an ensemble algorithm that constructs a series of regression trees using randomly sampled subset of training set for each tree and a subset of the availability tree after splitting with trees. For feature-weighted KNN, basically is the extended method of KNN and make decisions by identify the k-weighted nearest neighbors with the highest similarity with the test dataset. This feature-weighted KNN extends the standard Euclidean distance by using feature-weighted matrix, so to use the modified distance. We also use a t-test to determine whether different ODs have different travel times along shared routes. Using the t-test method, we obtain the p-values between different ODs. When the significance level is set to 0.05, a p-value greater than 0.05 means that there's no significance between the two ODs travel times. And a p-value less than 0.05 means there is a significant difference between the two ODs travel times. Here are our experimental results. So the first one is a base predictive model, and we have 3 lanes, 3 different problem types. So we have a 3x3, total 9 different models. For each model, we compare KNN and random forest. And here is the result. As you can see, the feature-weighted KNN achieved the best results for all the origin and the middle way problems. And random forest only shows the better results in day before problem type for all lanes. So the following table shows the detailed performance in terms of MAPE, MAE, and MSE for the origin problem type for all the lanes. As you can see, the MAPE is around 15 to 17% error. For middle way is even less, from 14 to 15% for KNN. For the day before, random forest shows the better results from 14 to 19%. Here is the base predictive model for empty directions. We only consider east lane and south lane for these 3 different problems, because for test dataset there's no empty for the west lane, so we didn't do that. And we find out almost all the problem type KN shows the better results. Only in the day before or for east lane, actually random forest is better. Here is the detailed results. As you can see, the performance is very similar to the loaded directions. It's around 14 to 19% in terms of MAPE. For middle way is from 13 to 18% for KN, the best results. For day before, for random forest is 17%. South lane is for KN is 11.8%. Random forest, south lane. Actually, east lane is random forest day before. For east lane is random forest. For south lane is KN. Sorry, yes, it is correct. It is correct. For enhanced predictive model, after we add in the GPS data, actually what we find is the model's performance actually decreased a lot, and especially in west lane. So before we add the GPS data, you can see the base predictive model is around from 12% to 18%. However, once we add this GPS data, and then our performance is drops to 20% to 30%. In the percentage error. For the special challenge for loaded direction, we did the t-test. Here is the p-value of the t-test results. As you can see, for OD1, OD2, OD1 and OD3, the p-value is very small. That means OD1's travel time is totally different than OD2 and OD3. So that means OD2 and OD3 are very close for the travel times. For the west lane, all the p-values is greater than 0.05. So that means all the travel time, OD4 to OD6, they're all the same, almost the same, no significant difference. So here is the detail, the CDF of the travel times, as you can see. So OD1, the green line, actually shows totally different, because both blue line and red line are under the green line. So you can see the green line is totally different. The west line, they are very close to each other. Although green line shows different, but in the front part is higher, in the later part is lower. In order to further explore the difference in the shared part in the east lane, we moved the endpoint of the shared part loaded and reduced the length of the shared route. As you can see, the east lane is from Fargo to Phi Side, and then from Fargo to Bergen. As you can see, all the ODs in the for OD1 and OD3, they are less than 0.05. So that means the travel time is different. And then we moved Bergen to Selkirk, and we also moved to the Buffalo. Until we move to the Buffalo, you can see, and the OD, the p-value is all greater than 0.05. That means from Fargo to Buffalo, in this shared route, the travel time actually are very close to each other. However, from Buffalo to Phi Side, this section shows a very large travel time differences. So here's the CDF plot and box plot from Fargo to Buffalo. You can see the travel time are very close to each other. And for empty directions, there's no significant difference between the three ODs, because all the p-values are greater than 0.05. So here is our conclusion. So in general, the feature-weighted KN is more accurate than random forest on most models. And also, feature-weighted KN achieved better prediction results in origin and middle way, while random forest showed better results in day before problem. The third one is the closer to the terminal, the higher the prediction accuracy of the model in general. The fourth one, the GPS data have a negative impact on the prediction accuracy, especially in the west lane. It is believed that GPS data contain many errors and do not provide much useful information for the presentation of ETA. As for the special challenge, the largest factor that caused the significant difference in shared part of the three ODs of the east lane loaded direction is the section from Buffalo to Phi Side. In contrast, there is no significant difference among the three ODs of the west lane's loaded direction among the three ODs of the east lane's empty directions. We also received some review comments by the committee. So here we address them one by one. So the first one is show an example of feature-weighted KN. Here we picked the test train of 39. The direction is from Strathcole to Plains. Departure time is 2016, July 25th. So we use the training set. This is our training set. And then we calculate the nearest distance for all the trains for each section, each station segment. And then for each station, actually, we determine our nearest neighbor for the train ID. As you can see, the nearest neighbor for train ID is showing as a red column here. Whatever, if you give me the one remaining station, and then I will use this train ID for the rest of the prediction. The average map is around 17.8. percentage. Here is the remaining part of this table for all the remaining stations, 18 stations. The second one is the feature weighted calculation and actual weights for the FWKN. So we have 3 steps. First, we draw up the weights of according to the feature importance of given by the random forest, and we update the weights iteratively. We use the orthogonal experiment method to reduce the number of updates. As shown in the following table, we finally select a group of weights with the highest accuracy. Actually, our weights given to these top 3 features. The first one is remaining distance. The second one is remaining number of stations. The third one is the cumulative distance traveled. 2.2. Why this is better than just normalize all the features as is typical done for KN? Because traditional KN, they treat all the weights. The weights equals to 1, right? But the feature weighted KN, they consider the weights of features and makes the prediction accuracy better because it adds more dimension for the parameters. The third one, how we use the shared parts and not shared parts in the estimation process. We take a western region, a west lane as an example. According to the fifth conclusion, actually the travel times of shared parts of eastern and western region within their respective region is very close. So the routes of the eastern and the western region can be used in a single model. So the shared part we consider just together for this region for particular model. Of course, we separate for the empty and loaded directions. The fourth one is what is the processing of the data from all different rail cars. We have 2 steps. First, after iterating the data generated by all individual rail cars of a train, we find that the data contains a large amount of repeated information and a small amount of errors in a single car. So we select the most frequent arrival times of individual rail car as the train arrival time, while the arrival time of other individual rail cars will be discarded. In this way, the dataset is simplified, which not only reduces the time of model analysis, but also improves the accuracy of the model prediction. The 5.1 commands how do you do the selection application of the hyper parameters of the random forest model. Actually, we just do experiments and try different combinations as we did for the parameters for the weights, the feature weights of KN. We try different combinations. We found the 120 for the number of estimators is the lowest error, and 15 as the steps of the trees is the lowest, gave us the lowest error. So here is our results, and the first table shows the different number of estimators for 110, 120, and 130. As you can see, the map is the lowest for 120. And also for the next one table shows the maximum depths for 18, 15, and 12. As you can see, 15 shows the best results. For 5.2, the comparison of the K4 cross-validation and out-of-bag estimate. So the selection of different training set tested has a great impact from the prediction results. Compared with the out-of-bag estimate, K4 the cross-validation is more universal and reducing the uncertain of cost-bag dataset partition. So in our experiment, the prediction accuracy of out-of-bag estimate may change with different selection of random seeds. So in this case, compared with the out-of-bag estimate, K4 cross-validation can evaluate the performance of the model more stably, and we believe. The sixth one, so what is data input and whether we used all the trains within a lane. So actually the conclusion is yes, we used all the train data in each lane for prediction. So after processing the dataset, the number of train samples is too small, so we took the information of each station as the sample in this way. The data information for each train will generate multiple site samples and will increase the sample dataset for the dataset. Then we concentrate the train data in a region or in a lane to improve the data volume of the input samples so as to ensure that there's enough data to divide the training set and test set when building the model. The processing and the impacts of the GPS dataset. So we have 3 steps. Firstly, the format of GPS data is similar to that generated by the station report. So we regard the GPS data as a new station. The second step, we calculate the distance between 2 adjacent stations according to GPS segments and compare it with the distance of real stations. The last step, actually, the GPS data with the large errors are discarded. Okay, here's all our presentation. Thank you for your attention.